Ladies and gentlemen, welcome to today's topic, aliens. Are they real? Do they exist? And if so, what do they look like? Today, we will dive deep into the topic of aliens, exploring various theories and facts about these mysterious creatures. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Here are a few theories about aliens. Extraterrestrial life exists. This is the theory that life exists elsewhere in the universe, perhaps even within our own solar system. Microbial life could potentially exist on Mars, or some of the moons of Jupiter and Saturn, for example. More complex life forms, such as intelligent civilizations, could also exist on planets orbiting other stars. The Fermi paradox. The Fermi paradox suggests that if intelligent life is common in the universe, why haven't we detected any evidence of it? Some theories suggest that intelligent civilizations tend to self-destruct, while others propose that they are too far away or have no desire to communicate with us. Ancient aliens. This theory suggests that aliens have visited Earth in the past and have influenced human history and culture. Proponents of this theory point to ancient artwork and texts as evidence of alien visitation. UFO sightings. Unidentified flying objects are often cited as evidence of alien visitation. While many sightings can be explained by natural phenomena or human-made objects, some remain unexplained and could potentially be evidence of extraterrestrial visitation. The simulation theory. This theory proposes that our entire reality is a computer simulation created by an advanced civilization. While not specifically about aliens, this theory suggests that the creators of the simulation could potentially be an extraterrestrial civilization. To start with, let's address the most basic question: do aliens exist? Well, according to the Drake equation, which was developed in 1961 by astronomer Frank Drake, the probability of intelligent life existing elsewhere in the universe is high. The equation takes into account factors such as the number of stars in our galaxy, the number of planets that could potentially support life, and the probability of life forming on those planets. Using these factors, the Drake equation estimates that there could be millions of intelligent civilizations in our galaxy alone. But the question remains, have we ever encountered these civilizations? Many people believe that we have, and there are countless stories of alien sightings, abductions, and encounters. However, there is little concrete evidence to support these claims. So, let's explore some of the most popular theories about what aliens might look like. The traditional image of aliens as small, green, big-eyed beings is a product of popular culture. However, it is unlikely that aliens would look anything like this. In fact, it is impossible to predict what aliens might look like, as their appearance would depend on the conditions of the planet they evolved on. For example, if an alien species evolved on a planet with high gravity, they might have shorter, stockier bodies. If they evolved on a planet with a harsh, radiation-filled environment, they might have evolved to be more resilient to radiation. It's also possible that some alien species might not even have bodies as we know them. They might exist as pure energy or as a hive mind collective. But why would aliens visit Earth? There are a few possible reasons. Some scientists speculate that aliens might be interested in our planet because of its unique location in the universe. Earth is in a Goldilocks zone. It's not too hot, not too cold, and has the right conditions for life to thrive. Aliens might be interested in studying our planet to learn more about how life can survive in these conditions. Another reason aliens might visit Earth is to make contact with us. If there are millions of intelligent civilizations in the galaxy, it's possible that some of them are trying to communicate with us. However, if this is the case, they might be communicating in ways that we can't even comprehend. Their methods of communication might be vastly different from ours. So, what should we do if we ever do encounter aliens? Many scientists believe that we should approach any encounter with caution. We should avoid making any sudden movements or aggressive actions, as these might be misinterpreted by the aliens. Instead, we should attempt to communicate in a peaceful and non-threatening manner. If we do make contact with aliens, it could have profound implications for our understanding of the universe. It could challenge our beliefs about our place in the cosmos and force us to confront some of the big questions about life, the universe, and everything. Now that we've explored some of the theories and possibilities of alien life, let's consider the idea of the Fermi paradox. This paradox asks the question, if there are so many intelligent civilizations out there, why haven't we seen any evidence of them? Why haven't we detected any signals or observed any spacecraft from other worlds? One possibility is that advanced civilizations tend to self-destruct. With technology comes the potential for destruction, whether through environmental damage, war, or some other catastrophe. It's possible that many intelligent civilizations reach a point where they are unable to sustain themselves and ultimately fail. Another possibility is that intelligent civilizations have no desire to make contact with us. Perhaps they are simply not interested in Earth or in communicating with other species. Or perhaps they are too far away to detect our signals and we are too primitive to detect theirs. Regardless of the reasons, the Fermi paradox remains a mystery and a subject of much speculation. But let's turn our attention to the possibility of life in our own solar system. While we haven't found any evidence of intelligent life, there are some promising signs that microbial life might exist on other planets or moons. For example, NASA's Mars rover has detected methane on the planet's surface, which could be a sign of microbial life. And scientists have found evidence of subsurface oceans on some of Jupiter and Saturn's moons, which could potentially support life. If we do find evidence of microbial life in our own solar system, it would be a major discovery and could have significant implications for our understanding of life in the universe. Let's consider the potential implications of discovering intelligent life. If we were to make contact with an alien civilization, it could have profound impacts on our society and our understanding of the universe. For one, it could challenge our existing beliefs and worldviews. We might need to reevaluate our ideas about our place in the cosmos, our religious and philosophical beliefs, and our understanding of the origins of life. It could also raise questions about the ethics of interacting with other intelligent species and the responsibilities that come with such interactions. Another potential impact is on our technology and scientific progress. If we were to encounter a more advanced civilization, we could learn from their technology and knowledge, potentially accelerating our own progress. On the other hand, it could also pose a threat if the aliens have hostile intentions towards us. It's difficult to say for certain whether aliens, if they exist, would be dangerous to us. We have no concrete evidence of intelligent extraterrestrial life, and so any speculation about their intentions or behaviors is purely hypothetical. Some people argue that aliens could be dangerous if they are more technologically advanced than us and have the ability to conquer or destroy us. Others point out that any civilization advanced enough to travel through space would likely have a more sophisticated understanding of the universe and may be more peaceful and cooperative. It's also possible that aliens could be indifferent to us, simply observing us from a distance without any intention to interact with us at all. Overall, while it's fun to speculate about the potential dangers of alien life, The truth is that we simply don't know enough to make any definitive conclusions about their intentions or behaviors. The search for extraterrestrial life should be approached with an open mind and a healthy dose of curiosity rather than fear or paranoia. Regardless of the potential impacts, the search for intelligent life continues. We are constantly developing new technology and refining our techniques to search for signals and evidence of other civilizations. And while the chances of finding intelligent life may be slim, the pursuit of knowledge and discovery is a worthy endeavor in and of itself.
The Cassini space probe approaches the ringed planet Saturn and its 56 moons. It discovers something almost unimaginable: conditions that might support life. And if those conditions could exist so close by, what might we find in the next galaxy? On a planet just like Earth. For millennia, we humans have looked to the skies and wondered whether we're alone in the universe. Today, we're closer than ever to knowing the answer. Some scientists believe we'll get our first look at our extraterrestrial cousins in the near future.
I hope it's in the next 10 years, and I'm ready for it next week. So, the sooner the better.
What's more, we could find these aliens not on distant planets in unexplored galaxies, but right next door in our own solar system. Scientists are now honing in on proof that ET is out there and living on the most hazardous of worlds. Our safari will journey to 7 destinations in our solar system to see just where these creatures could be and what they might look like. These exotic lands are unimaginably harsh. Life as we think of it would perish in an instant. But alien life may be far tougher than we expect, as we're learning from a surprising group of living things right here on Earth. Until just a few decades ago, we were sure our planet was unique. It is the only one we've found so far that has nurtured the evolution of millions of species. Thanks to its abundant sunshine, warm water, and protective atmosphere. We logically concluded that life needed each of those things, a conclusion that ruled out all other known worlds in our solar system. But then, biologists began combing some of the Earth's darkest and coldest places. And to their surprise, they found living, breathing creatures. Biologists call these organisms extremophiles. Some don't need light or oxygen. Others survive in tremendous atmospheric pressure. It seems life can turn up practically anywhere. Take Antarctica. After years of searching this arid, frozen landscape, scientists doubted they'd find anything alive. But in 1999, a team of explorers unearthed a rock from 6 feet under the ice. What they found amazed them. When they cracked the rock open, they found it teeming with tiny creatures. Here, at temperatures of 68 degrees below zero and 6 feet under solid ice, life had found a foothold.
Biologists have been increasingly discovering life, not kangaroos, but, simpler forms of life that live at very cold temperatures, very high temperatures, very great pressures, even in places where there's sort of a high degree of radiation. It turns out life is able to live in a much wider variety of environments on our own planet than we used to think.
And if life can survive extreme conditions, not just here at home, but elsewhere in our solar system, think of what this could mean.
Unless there's something extraordinarily miraculous about our solar system or our planet, then life has got to be extremely commonplace. I mean, there's got to be large numbers of worlds with life, and some of them would have cooked up intelligent life.
In the beginning, our Earth was as deadly a planet as any. Over the first billion years of Earth's existence, cosmic debris pummeled it mercilessly. The impacts turned its surface into a broiling, seething inferno where life was impossible. But once the solar system settled down and the Earth began to cool, water appeared, setting the stage for life. In 1953, researcher Stanley Miller proved in a lab experiment just how easily life on Earth got its start. He combined water with hydrogen, methane, and ammonia, components of the Earth's early atmosphere. Then he zapped his solution with an electric charge to simulate lightning. His results shocked the world. Miller had created organic molecules called amino acids, the protein building blocks of all living things. If lightning helped jumpstart life on Earth, could it have done the same on other planets? Galactic probes have now found the ingredients in Miller's experiment throughout our solar system, including one essential to life.
One of the requirements that every form of life that we know about on Earth has, every single one, is liquid water. We've used evidence for liquid water to kind of guide our search for habitable environments.
Our safari is headed to 7 worlds, some possibly rich in water, where scientists believe aliens might be hiding. While any life there might have begun much like life on Earth, how it looks now is anyone's guess. We begin in the world that has always fired our imaginations, the planet right next door, Mars. Of all the planets where we've looked for life, it's the one we've studied most. The scientist who may get the first look at Martians, if they're found, is Steve Squires, principal investigator for NASA's Mars rovers.
Mars has always had, among all the planets, I think, a special fascination for humans. For a very long time, we've known enough about Mars to know that it is probably the most Earth-like.
It may be the most like Earth, with an atmosphere and seasons, but we humans would perish quickly on Mars. Its air is thin, 40 times thinner than the air at the top of Mount Everest. And it sits in a bad neighborhood of our solar system, near an asteroid belt. Its atmosphere is too flimsy to protect it. Asteroids continually bombard its surface. Violent winds can whip Mars's sandy soil into storms that consume the entire planet for weeks and spawn tornadoes 8 kilometers high. Midday temperatures at the equator of 1 degree Celsius fall to -70 at night. David Grinspoon is a curator of astrobiology at the Denver Museum of Nature and Science. As he sees it, Mars would be warmer if it wasn't a planetary runt.
When I grab coffee on a cold morning, I know that a small espresso is going to cool off quickly, whereas a larger coffee is going to stay warm much longer. Large objects stay warm longer because their interiors are shielded from the outside where the cooling occurs. And planets are exactly the same way. A small planet will cool off early in its history. A larger planet like Earth will stay warm for billions of years, which makes it a better place probably to look for life.
Despite Mars's drawbacks, it has always fascinated scientists because its terrain seemed to give evidence that it might support life. Its dynamic landscape of mountains, volcanoes, and deep ravines is not unlike our Earth. To early astronomers, these features look like oceans and rivers, and even a system of canals, supposedly not just supporting life, but actually produced by it.
Percival Lowell in the United States observed these things and inferred that, in fact, these things were so straight and so regular in geometry that they had to have been the product of intelligent life. Okay? Well, he was right. The problem was the life was at the wrong end of the telescope. In viewing this thing visually through a telescope eyepiece, the human eye-brain combination started to connect things that weren't really there.
Lowell was not alone. Some scientists were shocked when the probe Viking 1 beamed back this image. Is that a human face? Perhaps produced by Martians in their own likeness? Until recently, we've never really known where to look in our solar system for extraterrestrial life. But we've always known what the aliens would be like once we found them.
Consciousness. I was on a table.
Usually, there is more than a hint of the Earthling in our aliens. Hostile or lovable, they tend to resemble mutant images of ourselves. As a senior astronomer at the Search for Extraterrestrial Intelligence Institute in California, Seth Shostak has spent his career listening for the radio waves of a distant alien society.
There's no reason to assume that they're going to look like us or even think like us or behave like us or have language. You know, you just have to look at the variety of life on Earth and you see that, you know, nature can come up with lots of different forms.
But if there is life on Mars, how could it survive in such extreme conditions? Since the 1960s, scientists have sent dozens of probes to the Red Planet. The first pictures of the barren landscape quickly dashed any hope of finding intelligent beings. But what scientists did see startled them. Though there's no evidence of Martian-made canals, there are signs that Mars actually may have had water. Some think the angry red planet might once have been blue.
You just have to look back a couple of billion years, 3.5 billion, 4 billion years ago. Mars had a thicker atmosphere, had water on its surface clearly, maybe it developed life. And as it slowly went bad, you know, the life had to adapt.
Life may have adapted, not died off, because some liquid water may still exist underground. But with no surface water, frigid temperatures, and ultra-thin atmosphere, Mars is a planet only one kind of creature could love, an extremophile. Extremophiles thrive in the cruelest of places. To see where they might lurk on Mars, we head to the Valles Marineris, a massive rift in Mars's surface, 20 times wider than the Grand Canyon in places, and almost as deep as Mount Everest is tall. Lakes may have once flooded this valley, and those lakes could have hosted life. As the water dried up, life could have evolved to cope with the harsher environment. We won't know what these extremophiles are like until we find them. But they may resemble creatures that exist in extreme places right here on Earth. An unusual team of biologists, called astrobiologists, study Earth for the kinds of life we may find in outer space. Astrobiologist Rocco Mancinelli is on the hunt for Mars's extremophiles.
If it went beneath the surface, and some of it undoubtedly did, then what happened to it? Well, it formed brine pockets. So what kind of organism can live in a salty brine? A salt-loving organism.
Astrobiologist Chris McKay thinks he knows the kind of salt-loving creatures that might survive on Mars. Creatures much like those he's found in one of the driest, saltiest places on Earth.
The fundamental challenge to life on Mars is, in a sense, the fundamental challenge of life here in Death Valley. It's dryness. That is the hardest thing for life to adapt to.
Thousands of years ago, a salty lake covered Death Valley, just as lakes filled Mars's Mariner Trench.
Move in closer. This is still wet, a little wet.
This appears like a lifeless place, a big, flat, white, empty horizon. But yet, just below the surface, we find layers of algae and bacteria growing. They're living in an environment that in many ways is fundamentally different from the environment that we sense on the surface. Here you're in a place which looks lifeless, looks dead, and yet you dig down and hidden underneath, there it is.
Beneath the salt is a layer of hardy green algae that survive on the water and light that trickle through. The algae in turn feeds salt-loving microorganisms.
Here in deserts on Earth, dried, salty lake beds, we're going to find them on Mars as well.
Salty deserts are not the only places life might be hiding on the red planet. There are Mars's tremendous volcanoes, some of them 6 times larger than those on Earth. Astrobiologist Penny Boston studies the caves, called lava tubes, left over after volcanic lava has dissipated. Not long ago, we assumed caves like these were devoid of life. They get no sunlight, and no sunlight means no photosynthesis. But in lava tubes outside Albuquerque, New Mexico, Boston has found evidence of extreme life.
Because we know Mars has many, many lava tubes. And so here we have the opportunity to see how these formed and also to look at the life that inhabits them.
The extremophiles Boston has found appear to be thriving. They get their energy by feeding on the minerals in the cave wall.
So here we're up close to the wall, and you can see these white patches here growing against the black basalt. And each one of these is like a major city for these little guys. And they're all nestled in these little pockets in the basalt. And so these guys are permanently adapted to these freezing temperatures. They never see any light, and they get what they can find in the environment.
Are there creatures like these in the caves below Mars's volcano fields? Boston thinks so.
We are going to find life, and I just hope that I live a long and healthy life so that I can still be around to see that.
We may already have had our first glimpse of Martians, not from our visit to their planet, but from their visit to ours. 16 million years ago, an asteroid slammed into Mars and propelled a 2-kilogram rock into space. Amazingly, that rock sailed to Earth and came to rest in Antarctica. Inside, NASA scientist David McKay and Everett Gibson were amazed to spot the outlines of fossils. Water has carved small tunnels in the rock. And in these tunnels, McKay and Gibson found what they believed to be evidence of bacterial life.
These are little microbes, and they're dead, and they're fossils, or in some cases, we don't even see the forms. We see the footprints or the evidence that they were there.
Life from Mars? Maybe. The hunt is only just beginning. NASA plans to send a rover called Phoenix to Mars. It will study the planet's ice cap and probe 3 feet beneath the surface. NASA even has a plan to send human visitors. They may not meet the little green men of our imaginations, but they could encounter life in some form. What will it look like? It is likely to be a subterranean dweller with an ability to survive on little water. Perhaps an organism with a taste for minerals, like the creatures in the lava tubes of New Mexico. Even the smallest find would have enormous implications. Proof that life is not unique to Earth, but exists just next door. Our safari to the places in our solar system likely to harbor alien life now takes us past the asteroid belt on the far side of Mars. Here, Jupiter reigns. But this planet, the largest in our solar system, is fairly hostile to life, thanks to its toxic gases and overpowering gravity.
Not only is it pretty cold out at Jupiter, it's also, it's got this really thick atmosphere, tens of thousands of miles thick, and it's got ammonia and methane and, things used to clean the bathroom. But Jupiter has more than 60 moons that we know about.
At first glance, those moons would seem unlikely places to seek alien life. Their atmospheres are thin, and they are inhumanly cold. The temperature on Callisto is lower than minus 200 degrees Celsius. The scientific probes Voyager and Galileo have detected little on the surface of these moons but ice, with one dramatic exception. Io is one of the closest moons to Jupiter. When NASA sent Voyager 1 to Io in 1979, astronomers were astonished to find its surface roiling with giant volcanoes.
Io is the most volcanically active place in the solar system, just spewing volcanic material from its surface all the time.
What could be heating the interior of this frigid moon? Amazingly, it's the force of gravity from Jupiter. The giant planet exerts enormous gravitational pull on its moons. The closer the moon, the stronger the force. So strong, it can actually stretch their crusts. But some of these moons have elliptical orbits, so as they near Jupiter, the crust stretches towards it. When they move further away, the crust relaxes back towards spherical. This constant tidal movement creates friction deep inside, and that friction generates heat. It's like rubbing two sticks together to start a fire. The pull of Jupiter is heating Io from the inside out. Volcanic fumes and lack of water make Io inhospitable to life. But Jupiter's other large moons are more distant, close enough for Jupiter's gravity to warm them from within, but distant enough to remain calm on the surface. 3 of them look particularly promising as possible homes for alien life. The one furthest from the giant planet, Callisto. On its surface, Callisto looks like our moon, scarred and cratered by countless hits from asteroids. Those impacts may have melted the surface ice for brief periods, allowing life to take hold. But in 1998, the Galileo spacecraft detected a much more promising incubator deep beneath Callisto's surface. Radioactive rocks and tremendous pressure in its core generate heat inside Callisto. The heat may be melting its icy crust from below, creating a hidden ocean. And hidden oceans could mean hidden life. As we fly closer to Jupiter, we find its largest moon, Ganymede. Ganymede is also deeply scarred. Ridges rise above its surface. Those bright spots are craters as big as 5 kilometers across and likely to be lined with frost. But these photos offer the most compelling clues to where life here might hide. They show flowing glaciers, glaciers that resemble those on Earth. Ganymede's moving glaciers could also be signs of heat within. So, like Callisto, Ganymede could also have a hidden ocean, buried beneath as much as 190 kilometers of ice. The third moon on this leg of our alien safari is the most intriguing. It is called Europa, and of the three, it resides closest to Jupiter. That proximity to the giant planet means Europa's core may be very hot, far hotter than Callisto's or Ganymede's. But its surface remains frigid, a potent combination for life, since there could be a temperate zone where they meet. Mammoth fissures scar Europa's thick crust of ice, a sign that ice is always shifting. On our own planet, we see the same cracks in the ice sheets covering the Arctic Ocean. Europa's crust may be riding the largest ocean in the solar system, an ocean twice as large as all of Earth's put together.
Now those oceans, if they're there, and the chances are pretty good that at least some of them are, they've been sitting around for a long time, 4 billion years, a little longer, right? In 4 billion years, an ocean of water, do you think anything might have cooked up there? Well, it certainly seems plausible.
The environment in Europa's ocean is more or less as nice as the environment in our own ocean, as a place for living things to exist. Heck, things from planet Earth could probably live in the European ocean.
But Europa's oceans will be very cold, even slushy. And sunlight never penetrates them, thanks to an icy cover that may be 16 kilometers thick. We might never have thought life could exist here if not for a revolutionary discovery off the coast of Ecuador. Deep in the Pacific, biologists have found flourishing communities of tube worms, crabs, and even squid. These creatures are thriving despite complete darkness, extreme cold, and the pressure of the deep ocean. They feed on bacteria that take their energy not from the sun, but from chemicals erupting from the sea floor. We might find very similar volcanic vents on Europa, supporting their own web of life. To find out, NASA scientists would like to put a lander on the European surface. Some would like to send a cryobot, a robot that would melt the ice and release a probe into the liquid below.
That's not so hard to do. You just have to melt your way through. But you're going to have to melt your way through not a couple hundred feet, but maybe a dozen miles of ice. And send down a fishing line with maybe a video camera and a light bulb on it and look around.
In all that water, we can't rule out the possibility that very simple life forms have evolved further. We might even find creatures as advanced as some here at home. Most likely, however, we would find microbes. But even that would be a sea change in how we view the birth and growth of life. Europa was warm. What if a place is one of the coldest known? Or if its lakes flow with toxic chemicals instead of water? These are the worlds we find as our safari continues even deeper into space. As our safari in search of alien life sweeps by the ringed planet Saturn, we can see the violently swirling gases that choke its atmosphere. We can also feel Saturn's gravity, weaker than Jupiter's, but still formidable. We'll keep moving. We're not likely to find living things here. Saturn's rings are also extremely inhospitable. They're made of rock and ice, as small as a grain of sugar or as big as a house. But Saturn has many moons, 56 that we've spotted so far. Our safari heads first to one of those moons, a tiny frigid satellite called Enceladus, just 500 kilometers in diameter. Here, gravity is very weak, a fraction of that on Earth. And Enceladus has hardly any atmosphere. It reflects back into space almost all the sunlight that hits it, making it the shiniest object in our solar system. Until very recently, we also thought Enceladus was too cold to support life. It appears we were wrong. In 2005, after a 7-year journey, the Cassini spacecraft approached the tiny moon and detected something that stunned the mission's principal investigator, Caroline Porco.
So this was the picture that just, grabbed us. Just was shocking.
Those are plumes made of water from a geyser. The geyser's steam and hot water hit the cold vacuum of space and explode into a jet of ice. With little gravity to rein it in, the ice cloud can grow as big as Enceladus itself. Porco has never seen anything like it anywhere else.
It's like a planetary explorer's dream to come upon a body like Enceladus. Those jets, those fountains, if you will, just spewing vapor and icy snow hundreds of kilometers above the south pole of Enceladus.
There's only one conclusion. Tiny, frigid Enceladus is piping hot within. Like Jupiter, Saturn's giant gravitational field tugs on its satellites, creating friction and heat within.
As far as we can tell now, it seems like an inescapable conclusion that there may be liquid water deeper down on Enceladus because it's warm. And the best models we can put forth right now to even explain the warmth, much less the jets, seem to indicate that you would get temperatures warm enough to melt water.
Heat, liquid water, even the furthest reaches of our solar system may contain the chemistry for life. What kind of creature could live in the steamy waters of a geyser? Thanks to hot springs back on Earth, we have some idea. At one point, we assumed nothing lived in the steam-driven fountains of Yellowstone National Park. But then, biologists discovered microbes in these waters. Microbes that feed on chemicals dissolved in the water. Today, we call them thermophiles. The hardiest can thrive in boiling water. Could there be thermophiles on Enceladus? To find out, our safari takes us in for a close-up of this extraterrestrial Old Faithful. It's too cold for anything to live near the surface, but temperatures there are minus 165 degrees Celsius. But what about the hot water inside? In the ice plume above Enceladus, Cassini's probes have found carbon dioxide and methane, chemicals that could feed life below. Just as the chemical-laden springs of Yellowstone feed microbes living there.
We have a body that very, very likely has liquid water in its interior, has shown us already it's got simple organic compounds and, a whole host of things that make it, I think, a major body of astrobiological interest in our solar system.
If Enceladus has been a shock, astronomers have been astounded by another of Saturn's moons, Titan. It may be the unlikeliest to harbor life. Titan gets only a limited amount of sunlight, about 1,000th as much as Earth. Probes sent to Titan have detected ice, but no liquid water. And at temperatures of minus 138 degrees Celsius, that ice is hard as stone. What could possibly make Titan a promising environment for alien life? Remarkably, Titan in many ways resembles the Earth, but not the one we know now.
Titan has turned out to be the body fantastic in the Saturn system, which is long suspected of having an environment at the surface, not only similar to the kind of environment we find here on Earth, even, believe it or not, similar to the kind of environment we had on Earth before the emergence of life.
Titan intrigued Carolyn and Porco's team so much, they directed the Cassini spacecraft to send a probe there in 2005. It was the most distant surface mission ever conducted. The probe saw just ridges and plains. But a later flyover by Cassini spotted a shoreline. Soon, thousands of lakes came into view, at least one bigger than the Great Lakes of North America. It's the first time we've ever detected liquid on the surface of another celestial body.
Kind of looks like Minnesota, except the lakes are not water, they're liquid natural gas. But liquid natural gas is a liquid.
And that's not snow. Those are methane flakes. Like Earth, Titan has weather, but it's of a rather psychedelic kind. There are even methane hurricanes.
It's not water, it's methane, doing all the exact same things. Raining, evaporating, flowing in rivers. So you have something that is basically doing what water does on Earth, on Titan, only it's methane.
A similar scene may have existed on Earth 4 billion years ago, making scientists suspect that Titan could also be an incubator for life.
Chemistry does go on. At those cold temperatures, it's really slow. But Titan has had 4 billion years in which to do some chemistry, and maybe in that period of time, maybe something is cooked up.
It would have to cook up without liquid water, something we've never seen before. But scientists aren't ruling it out. The substitute could be the methane, so abundant on Titan. Used for fuel on Earth, methane was long thought poisonous to all life. But in 1997, researchers examined mounds of methane ice in the Gulf of Mexico, and they were astonished to find colonies of small centipede-like worms thriving amid the frozen substance. They think the worms may eat bacteria that feed on the methane.
In general, things that we think of as deadly, many of them are potentially lively if you can figure out an evolutionary way to tap into that energy rather than having it destroy you. Then it can be bountiful.
There could be one more complication for life on the surface of Titan. With only a weak magnetic field to shield it, living things on the surface could be exposed to cosmic radiation. But that might not be a problem for an extremophile, as we found here on Earth. Biologists have uncovered plenty of life near Chernobyl's contaminated nuclear reactor, and even swimming in toxic radioactive spills, actually feeding off the decaying molecules. It's possible Titan's life forms could do the same. To find life on Titan, we may have to dive into its methane lakes, where we might find chemical-loving bacteria. We may even find microbes resistant to radiation, not unlike those here on Earth at Chernobyl, living on its rock-hard ice sheets. Organisms that eat methane might give off heat, melting the ice, possibly creating another fountain for life. There's no doubt, life on Titan would be a strange brew. But we have yet to visit the most bizarre world where scientists believe life could exist, and it's much closer to home. Our safari of the world's most likely to harbor alien life has taken us far. We've visited frigid deserts, submerged oceans, and methane lakes. But the world we are about to visit may be the most extreme of all. For our final stop, we are turning back toward Earth, to Venus, our closest planetary neighbor in the solar system. If life can survive here, it seems it could exist almost everywhere. To reach the surface of Venus, we have to fly through a dense layer of yellow clouds, 64 kilometers deep, with a composition similar to battery acid. The atmosphere here is 90 times heavier than Earth's, too heavy for a human to tolerate. On the ground, there are extinct volcanoes and lava flows as far as the eye can see. They cover 85% of the planet's surface. It is hard to believe Venus once had vast oceans.
You basically had a runaway greenhouse effect, where as it starts to get warmer, the oceans start to evaporate, and then that puts water vapor in the air. Well, water vapor is a potent greenhouse gas, so that's what leads to the runaway. The oceans basically boil off, and then the CO2 all ends up in the atmosphere, and so today you have this very hot, hyper greenhouse planet.
With temperatures around 460 degrees Celsius, Venus is even hotter than Mercury, the planet closest to the Sun. Not a surface hospitable to life.
Life as we know it cannot exist on the surface of Venus because organic molecules would just be ripped to shreds by the hot gases.
But we've stopped here not because of what's on the ground, but what's in the air. In 1982, the Soviet spacecraft Venera 14 visited Venus. In the clouds, 50 kilometers up, it detected temperatures much cooler than on the surface. What's more, it found the molecules so critical for life, H2O. So far, every bit of water we've found beyond Earth is frozen solid. Only in the clouds above Venus have we found it in vapor form, a possible incubator for life. But Venus's clouds are also filled with highly acidic sulfur. Once, we thought nothing could live in sulfur. But scientists have analyzed some of the most acidic water on Earth, leaching from a California mine.
Watch your head, sulfuric acid.
In sulfuric acid strong enough to erode metal, eat through clothing, and dissolve human flesh, they found life. Acid-loving extremophiles. These organisms feed on sulfur compounds, like iron sulfide, eating the iron and emitting the highly acidic sulfur. Do extremophiles like these float above Venus? Astrobiologist David Grinspoon likes to think it's possible.
Maybe in the clouds of Venus there are some sulfur-based organisms. Sulfur actually absorbs ultraviolet light in interesting ways, and I'm just imagining that there's maybe some kind of photochemical reaction going on where ultraviolet light is actually being used to convert chemicals into some higher energy state, which then is basically being eaten.
What will these aliens be like if we do find them? They would have to tolerate high temperatures and enormous atmospheric pressure. They would also need to thrive in acid concentrations deadly to most life forms. Perhaps they might resemble a hardier version of the acid-resistant extremophiles in California's mine.
We keep finding that life lives in places that we used to think were inhospitable. So whenever we say, oh, it's impossible, you couldn't have life in the clouds of Venus, I think we have to be very careful because they might just reflect our own ignorance or our limitations on our own imagination, and maybe not real limitations on the ultimate creativity of nature, which seems to find solutions to these problems.
As our safari returns to the cool, blue, lush and lively world of Earth, we can see why we so revere its life-sustaining gifts. But, as we are learning, even the most extreme environments can harbor living things. Extremophiles may resemble the first version of life in our universe, and they could even be the most common. Could they have evolved further from these humble beginnings? Could intelligent life be out there as well? For more than 40 years, scientists at the Search for Extraterrestrial Intelligence Institute in California have been searching the skies for answers to that question. Astronomer Seth Shostak believes he'll know the sound of alien life when he hears it.
We have a couple of observing projects to try and find signals. The biggest one are our radio searches, and that's where we use big arrays of antennas, and we point these antennas at nearby star systems that we think, well, this is the kind of star that might have a planet that might be something like Earth. We point in those directions, hoping to pick up a signal that would tell us that somebody there is clever enough to build a radio transmitter.
It's a safari that never leaves home. Astronomers have also recently captured enough light from planets in distant solar systems to deduce their chemical makeup. They have found elements that may help form RNA, one of the building blocks of life here on Earth. And 20 light years away, in the constellation Libra, a team of European astronomers has found a planet that could be warm enough to have liquid water on its surface, just like Earth. Meanwhile, headed to the furthest reaches of our galaxy are 4 spacecraft launched in the 1970s. Aboard 2 of them is a map of our solar system and the image of a man and a woman. 2 others carry a sample of uranium, whose rate of decay would date the probe, regardless of language. The 2 are also carrying what could be the most universal message of all, a recording that includes a composition by Bach. Just don't expect news anytime soon. These intergalactic postcards from the Earth will take 80,000 years to reach the nearest star. Our search for life beyond Earth has only just begun. There are billions of planets yet to be explored. Every one of them holds the tantalizing possibility of life. Even intelligent life.
Just in the face of this enormity, the idea that we're the only game in town, it just doesn't seem reasonable.
I think the question of whether we're alone is profoundly important for human beings in general. If you're aware, you really have to ask that question.
Somewhere in a galaxy known or unknown, something or someone could be looking out into space, peering at the Milky Way and wondering, is there life out there?
The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. This video lets you see some of the many things we do not understand in the universe and the strange and surreal paradoxes in what we think we understand. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Everything we know represents just 5% of the universe. What is the rest? Normal matter. Protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are 2 mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, width, and height, and 1 dimension of time, making a total of 4 dimensions in space-time. This is known as the 4-dimensional space-time. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions, but these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional space-time can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the four-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature. In certain situations, 2 particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet. Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us. But why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics, as we know them, break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in space-time. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us onto new and unexpected ways, spurring us onto new heights of discovery and understanding.
2017 was a busy year for scientists of all sorts, the professional and the enthusiast alike. From a predictable astronomical rarity to surprise discoveries deep underground. It was a year that saw long-held beliefs challenged by newly found wonders, breakthroughs that led to innovations, and a glimpse 130 million years into the past. In August 2017, alarms sounded at the most sensitive scientific devices ever constructed. In Washington State, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected faint disturbances from deep space. The signal also hit LIGO's sister facility in Louisiana. Gravitational waves had reached Earth.
Gravitational waves are ripples in space-time. Space-time is incredibly dense. So to cause ripples, you have to have some sort of object that has enormous gravity, like a black hole or a neutron star. And when these objects are rapidly accelerating, they bend space-time and create these ripples that then travel through the universe to our detectors on Earth, like the one last August.
On high alert, the LIGO team quickly reached out to Virgo, its European counterpart in Italy, who confirmed that they too had detected gravitational waves. And then, as if by destiny, the stars would align once more to pave the way to a groundbreaking discovery.
Just 2 seconds later, with the Fermi Gamma Ray Space Telescope, we detected a short, bright flash of high-energy light that we call a gamma ray burst. This alerted the entire astronomical community to the fact that something very exciting was happening.
Using data collected from LIGO, Virgo, and Fermi, 70 ground and space-based telescopes scoured the edge of galaxy NGC 4993, some 130 million light-years away from Earth, searching for a small flash of light amidst a sea of stars. It would take less than 12 hours after the alarms rang at LIGO for Earth to have visual confirmation of a never-before-seen astronomical event.
What we saw was the result of the merging of two neutron stars. When they merged, they created an explosion in space-time. Those ripples went out across the universe as gravitational waves and were detected on Earth. The matter involved gave off gamma rays and other forms of light.
Neutron stars are the collapsed cores of massive stars left behind after a supernova explosion. No larger than a mid-sized city, these dense stars have 10 to 60% more mass than our Sun. This pair of stars, 200 miles apart, were locked in each other's orbit for over 11 billion years. But as they started accelerating and moving inwards, their orbit quickened from 30 times a second to an astonishing and unsustainable 2,000 orbits a second. Then, 130 million years ago, they collided in a resounding explosion. Peering into the past, telescopes were able to see the remnants of one of the universe's most impressive fireworks shows. A bright flash of blue followed the initial explosion, growing redder and duller as the days passed, until eventually fading to black.
The conditions around these merging neutron stars have densities and temperatures completely unlike anything we can do on Earth.
the violent explosion was observed to have produced 200 Earth masses worth of gold and 500 Earth masses of platinum, revealing for the first time the origins of heavy metals in our galaxy.
We think that all the gold in the universe was formed in explosions of this kind. After the explosion happens, the gold is spread out into the gas and dust of the interstellar medium. Later on, that gas and dust collapses into brand new stars and brand new planetary systems.
And these weren't the first gravitational waves detected by LIGO this year. 2 separate events have been measured before, including a pair of monstrous black holes that collided to form a single spinning hole, 53 times more massive than the Sun.
We received a perfect signal from this last merger. It traveled 3 billion light years to get here. In any given galaxy, one of these events might only happen once every million years, but we're now able to monitor about 10 million galaxies at a time. It's a new type of astronomy.
But while we wait for gravitational waves that can open a window on the origins of our universe, volcanic activity off the coast of Japan is presenting scientists with a picture of Earth's early history, when land first rose from the seas. Violent eruptions spew a steady stream of lava and rocks, expanding the newly emerged island of Nishinoshima, 3 square kilometers, in just 5 short months this year. These most recent blasts stopped in August, but could resume at any time. Situated atop the junction of 4 tectonic plates, the Japanese islands offer stunning insights about the formation of a variety of landscapes. Analysis of Nishinoshima's magma shows it to be andesitic, similar to the composition of continental crust. Monitoring the growth of Nishinoshima, geologists hope to learn more about the forces that led to the birth of the world's 8 continents. Yes, not 7, 8. In February 2017, the Geological Society of America published a startling paper. Zealandia, Earth's hidden continent. Geologist Nick Mortimer was the lead author.
To discover Zealandia is to change the map of the world, quite literally. Beforehand, most people would say, yes, we got 7 continents, they could count them off. But now, the world map's changed and we've got an 8th one on there.
In the beginning, there was no search for Zealandia. Mortimer and his team discovered the shallow submerged continent while performing geological work aboard a research vessel off of New Zealand's coast.
And so what the various geological investigations have led us to is that we do have the components of a continent here. When you pull the plug on the world's oceans, you literally reveal the continent of Zealandia.
Mortimer and his team confirmed 4 geological markers, the qualifying criteria for a continent: height, a varied geology or diversity of rock types, a thick crust, and ultimately size. Is it big enough? Corroborating data include rock samples, ocean drill cores, and satellite microgravity measurements, translated into bathymetric or elevation maps of the sea floor. Situated between the Pacific Plate and the Australian Plate, tectonic forces squeezed Zealandia, raising out of the water what we know today as New Zealand. With 94% of Zealandia underwater, the islands of New Zealand and New Caledonia are just the tip of this continental iceberg. And measuring in at 4.9 million square kilometers, Zealandia is 6 times bigger than the so-called microcontinent of Madagascar, and more than twice as large as Greenland. which also happens to be attached to North America. To understand Zealandia's origins, we must travel back in time to the time of the supercontinent Gondwana, comprised of what we know today as Africa, South America, Antarctica, and Australia. When Gondwana split apart 80 million years ago, it was a bit like the stretching of bread dough in a kitchen.
And then you start to pull that big lump of dough apart. And if you pull slowly, some of those pieces will stretch and get thinner.
Just like Zealandia, which broke off and slowly sank because of its relatively thin continental crust.
It's not as thick as the main continents, but it is thicker than the ocean crust. And geophysicists know that when you have thin crust, it floats lower in the mantle, and so it sits lower elevation-wise, and that explains, in very simple terms, why Zealandia is so submerged. Now that we've got Zealandia in the scientific arena, we do hope to consolidate it and to promote Zealandia in New Zealand schools, first of all, and we hope to get it in atlases, on globes. We hope that Zealandia will become as common and well known as any of the other major continents.
Of course, the initial buzz about Zealandia can only help its name recognition.
The notion that something so big and so important could be hidden for so long, I think captured people's imagination.
Out of sight, out of mind, no more. Of course, not everything that's undetected is so obviously obscured. And one remarkable discovery this year offers clues about how some prehistoric creatures could hide in plain sight. In northern Alberta, Canada, the remnants of a 110-million-year-old dinosaur from the late Mesozoic era is providing the world with an unprecedented look at a new species, the nodosaur. A fossil so pristine and complete that it shows the texture, patterns, and color of a prehistoric giant.
The nodosaur is the best specimen we have, and it's the closest you'll come, until we find a better one, in terms of coming face to face with a dinosaur.
The nodosaur is next to surreal. A petrified beast caught by Medusa's gaze.
We knew it was good, but we didn't know how good it was. I think it's the best preserved armored dinosaur in the world. I'm calling this the Rosetta Stone for armored dinosaurs.
The anatomy of the new species has already given scientists clues to how these animals evolved, how they radiated and diversified through time. And it doesn't stop there.
The skin is preserved. It's not just the impression of the skin. We actually have some of the original biomolecules preserved. One of the cool things that they tell us for this specimen is that the animal had at least a component of reddish-brown pigment to its skin. The coloration aspect is very exciting. So it's cool to know what color it was, but it's actually more exciting when that has some implications for how the animal lived.
Researchers believe the nodosaur was darker on the back and lighter on its sides and underside, a method of camouflage called countershading.
Now keep in mind, this was a 5.5 meter long, 10.5 animal covered in armor, but it still has camouflage. And to us, that just illustrates how intense the predation was back in the Cretaceous. You had these very large meat-eating dinosaurs, and they would have also been very visual predators. So it actually kind of just shows you how extreme that ecosystem likely was back in the Cretaceous.
The plant-eating, slow-moving beast only stood a chance because of its impenetrable coat of armor.
We see 3 rows of osteoderms. Those are what are called cervical rings, and it's armor that would have protected the neck of the animal. And as we move to the side, we see this giant parascapular spine. It's basically a big armor spine coming off the shoulder, and it's about 0.5 meter long.
And the spectacular specimen still has many secrets to unveil. The next focus of study are the contents of the nodosaur's stomach.
In addition to having skin preserved all over most of the surface of the animal, we also have abundant gut contents, so the last meal of the animal preserved inside. And this is what that stuff looks like. So we're currently doing all sorts of work on this, geochemical work, histological work, and CT scanning, trying to figure out what these spheroid structures are. And there's been many ideas that part of the diversification of dinosaurs is tied to the diversification of flowering plants. And it would be great to see exactly which types of plants this guy was eating, and if that hypothesis makes sense.
We know what dinosaurs ate, how they fought, and now what they looked like. But there are still many questions to be answered. And Alberta might just be the place to find them. It's estimated that there are thousands of fossils hidden underneath the Earth. But when a 6-mile-wide asteroid struck the Yucatan Peninsula 65 million years ago, dinosaurs had nowhere to hide. And the resulting global cataclysm of earthquakes, firestorms, and tsunamis ultimately led to their extinction. Some animals, however, managed to survive. But how? Since its discovery in 1978, investigations of the asteroid's impact crater include data from seismic images and recently collected core samples from deep within the site at Chicxulub. The data paints a devastating picture of destruction and led scientists to create a broad new survival theory, focusing on habitat and diet adaptability. When dinosaurs perished and a vast new ecospace emerged, the surviving species expanded rapidly to fill it. This is called adaptive radiation. A recent study shows that 1 out of 10 frog species descend from the original 3 frog species that survived the Cretaceous-Tertiary extinction event. Frogs were able to escape extinction for a number of reasons. They live in an aquatic habitat that offered protection. Their small size and unique metabolism allow for better endurance of environmental stress. Eventually, when vegetation returned, they were able to diversify worldwide and adapt to new lives in trees. Birds, too, exhibited the same adaptive radiation around the same time. A newly found 62-million-year-old mousebird fossil in New Mexico helped paleontologists map the diversification of land birds, which can be traced back to 9 original ancestors which survived the event. Warm-blooded, birds' feathers insulated them from temperature extremes. Their small size and ability to fly allowed for easier escape from hostile and barren terrain. And their diet of seeds, worms, and insects gave them the edge after much of the Earth's surface plant life had died. In the end, the ability to adapt to changing conditions proved a key characteristic for the survival of many ancient animals, including our smallest mammal ancestors. Just as it may be for humans today, as we confront the challenges of climate change. The city of Miami Beach already knows what it means to wade through sea level rise. In recent years, residents have experienced elevated high tides at certain times of the year. Known as king tides, these events are clear evidence of incremental increases.
Right now, we are definitely witnessing sea level rise impacts, these high tide flooding events that are growing in severity, more often, deeper, more widespread. That's sort of a pattern that we expect will continue.
That means huge financial costs by the year 2100. Another predicts 2.5 million Miamians could become sea level refugees and leave the area. It's not only Miami. All around the world, sea levels are expected to rise. The question is, by how much? In adopting a multi-pronged approach, Miami Beach has committed $400 to $500 million to combat sea level rise, building water pumps and raising their defenses.
With the continued issue of climate change and sea level rise, we're seeing an increase of water level every year. We had to make changes to adapt to this future condition. What you're seeing here, we put a boardwalk initially to give some height, but we found that that wasn't protecting the city. What we've done here is we've increased the levels of our new seawall. The new wall you see in the background here is our new standards. This is good for approximately another 50 years, and we're going to see water levels challenging even that new seawall.
Raising its elevation, Miami Beach seeks to stay dry and take control of its future.
The city's philosophy, our culture, is rising above. We believe we can meet the challenge. And the challenge is not only in rising above, meaning elevation, it's rising to and withstanding the challenges that come with sea level rise due to climate change. As a city engineer, I have complete faith that we can win. We can mitigate. We can survive.
Of course, the Earth's oceans have risen and fallen many times during the planet's history. And new archaeological evidence suggests these shifting shorelines may conceal clues about the earliest Americans. Until just recently, archaeologists generally agreed that the earliest people to populate North America were the Clovis people, dating back to some 12 to 13,000 years ago. But a group of scientists in San Diego, California, have a different theory.
We have the bones, the fossils, the distribution, the rocks, the date. We have evidence for humans in North America 130,000 years ago. We realize that that is a startling claim.
But the scientific community is struggling with the idea that humans arrived in North America 130,000 years ago.
The study of early humans in the New World has been very political and very controversial for over 125 years.
It's an old mystery yet to be solved, deciding who got to North America first and when.
Welcome, and thank you for joining us this morning at the San Diego Natural History Museum as we share some exciting news about a discovery made right here in San Diego.
Well, back in 1992, Caltrans was doing improvements to State Route 54, which involved adding a couple new travel lanes. And Richard Cerruti, who's a field paleontologist here at the museum, was monitoring excavations on the very north side of the freeway alignment and saw this little puff of let's say, tusk material being scraped up by an excavator and said, "Stop, let me go look at this."
The bones that Richard Cerruti found belong to an ancient mastodon.
That's one tooth, and it's characteristic of American mastodon.
Were these giants sharing North America with early man 130,000 years ago? The answer may lie in the position of the bones and tools found at the site.
There are anomalous fragments of rock, anomalous fragments of tooth enamel scattered throughout the site that just don't make sense.
Could these stones amongst ancient bone remnants have been an early form of primitive tools?
And we felt that it was important to produce a map where we carefully plotted or precisely plotted the position of all the bones and the stones or whatever else is in there, so that we can understand what the general pattern is.
It's thought that the tools found with the mastodon bones were used for butchering the animal.
So this is one of the cobbles that we hypothesized was used as a hammerstone 130,000 years ago, where there was a carcass of a mastodon. These people were trying to recover raw materials from it. they had a problem. How do we break these bones? They look over into the active river channel, find some cobbles of the appropriate size and weight, bring them back to the site. And if you look closely, there's some striations coming off of that are indications of where this flake has come off.
The cuts in this rock led the San Diego team to conclude that these were actually tools used by humans. An idea that Demir says might not be so far-fetched. Dr. Stephen Holin is co-director of the Center for American Paleolithic Research in South Dakota. He was part of the team that evaluated the findings from the San Diego excavation site.
So what do we got in here, Steve?
Looks like vertebra.
It does.
I said, I can't get my mind around this. This site has to be really, really old, but yet here's evidence of humans. I said it goes against everything I thought I knew and everything I have ever been taught.
Holin evaluated the mastodon bones and the stone tools recovered from the excavation site.
We would take the drawers out of the cabinets in here and bring them in on this table and look through them, paleontologists and archaeologists together. Richard Cerruti came in, so there were 4 of us, my wife Kathleen, Tom, and I, and we would look through and we would look for these very diagnostic pieces. And one of the things that we got all excited about first were these cone flakes that form in a circle around the point of impact from the hammerstone. And based on the experiment that we'd done in Africa, breaking an elephant femur with a big hammer, we saw the same kinds of fracture patterns that we did experimentally.
Holin specializes in evaluating broken bones at archaeological sites, looking for human causes, as this video shows from a test he conducted in Africa 2 years prior to working on the San Diego project.
Oh my God. As we puzzled over this, we kept coming back to this one explanation that explains all the data, was that humans did this.
The detective work by the San Diego Natural History Museum team was capped by the age dating that Richard Cerruti had done to prove the age of the mastodon bones he discovered.
This is one of the specimens that he used in his analysis. He cored it and he also sliced it. And after analyzing over 100 microsamples from this specimen and 2 other specimens of bone from the site, yielded an age of 130,000 plus or minus 9,000.
So after the article came out, there has been no critic come out to say that the dating is incorrect. In fact, other specialists in uranium series dating have come out and said the dates look perfectly good. So we're very comfortable with the dates.
While humans' arrival in the Americas may have occurred earlier than previously thought, new dating of another paleontological find, found in a South African cave, could soon upend long-held theories about the evolutionary tree of primates and early humans.
When we actually got into the chamber and could start removing it, we realized that not only was there one individual lying there on the surface, but the floor was literally comprised of Homo naledi. There are thousands and thousands and thousands of remains down in those chambers, and all you have to do is sweep the surface off, and there they are.
So the first time I sort of slid through that hallway into the open area where the chamber is and sort of started looking around, you know, you're only wearing a headlamp, so you just see flashes, but every flash of my headlamp showed bone. So I think right at that point I realized that we had a lot more than the original photographs actually had portrayed, so that was pretty exciting.
Homo naledi isn't really similar to any known hominid species in its entirety of its package. You've got little bits and pieces of almost everything we've ever found. Parts of the skull, if you just look at it quickly, look a little bit like Homo erectus. Got a very small brain. Other parts of the skull look very modern, like Homo sapiens. It gets stranger and stranger as you move down the body. You get the ape-like shoulders. You get these more and more human-like arms, which end with a hand that's human proportioned.
I was actually at the London Natural History Museum, and Homo naledi was on the wall, and then there was estimated age between 1.2 and 1.8 million years. But then, when we actually did the scientific dating of those teeth, this is when things got very interesting, because then we got an age of 200 to 300,000 years old.
When we got a date It's much younger than that, 250,000 years, give or take. We realized that we were dealing with a primitive creature, almost like a time traveler, that had come down from deep times to a point where it is very possible that Homo naledi was in direct contact with the emergence of modern humans. We never thought that was possible in Africa. Until this moment, we thought that there was effectively, during that entire time period of the Middle Pleistocene, late Middle Pleistocene, one form, a big-brained form of Homo sapiens. Now there are two, and that adds incredible complexity to our record.
The world of Homo naledi and other early humans was different than it is today. A veritable Garden of Eden, teeming with life. Pure and free from pollution. Few places like this still exist, and most of them quite remote. But look just a few feet underwater and you can find one of the most productive and overlooked ecosystems on Earth. Scientists recently learned that seagrass meadows help scrub the surrounding water clean of bacteria from raw sewage and other pathogens. A recent study of polluted waters in Indonesia showed levels of harmful bacteria to be 50% less in spots with robust seagrass beds, leading to healthier fish and coral in the surrounding area. You see, seagrasses oxygenate the water, trap sediment that might otherwise float freely, and host tiny microbes that kill many harmful bacteria. Eliminating toxins improves the health of any system, and the workings of a human body is no different. In athletics, though, they say no pain, no gain. A nod to the physical effort required to increase endurance and enjoy the health benefits of exercise. But new pharmaceutical research also aims to make those benefits more easily accessible.
The potential benefit of a drug that can tune you up in the way in which you normally get tuned up by exercise could have really dramatic effects.
Playfully known as the exercise pill, the experimental drug shifts metabolism by triggering genetic instructions for the body to burn fat instead of sugar during exercise, something that doesn't normally happen until after extensive training and conditioning. Recent tests increase the endurance of otherwise sedentary mice, which also proved to be resistant to weight gain while on the drug.
We have two groups of mice, and one group on the drug, the other group as a control without the treatment of the drug. So we were quite surprised to see the astonishing results. The mice treated with the drug, they can run almost 100 minutes longer than the one that are not treated. The increase was around 70%.
Researchers ultimately hope their product can improve the health of the disabled, elderly, and obese.
There are many reasons why people can't either walk or run or exercise. And the idea is if you can bring a small molecule into the picture that can confer the benefits of fitness without training, you could really help a lot of people.
From energizing our bodies to powering societies.
So we are just waiting for the next experiment. It's going to happen in 10 seconds. There you go. You see the flickering of the plasma? We are creating fusion here. This is our little sun. It's extremely hot.
Each day, every 20 minutes, researchers build the sun. At the Culham Fusion Centre in Oxfordshire, Britain, generating temperatures greater than 200 million degrees. These nuclear fusion trials would be impossible without JET, the Joint European Torus, a donut-shaped plasma containment vessel.
At this point, we're the most important experiment in the world.
Thanks to JET, where energy is created by combining hydrogen atoms.
Right? There's heavy hydrogen, which we call deuterium, and the super heavy hydrogen, which we call tritium. And when they're running around at these temperatures, like 200 million degrees, they bang into each other with immense speed. And when they do, and they get close enough, what we call the strong force, which binds the nucleus of atoms together, grips them, pulls them together, and they fuse, and they make helium, and they spit out a neutron. Fusion really is the perfect way to make energy.
And yet, despite fusion's transformative potential to provide safe and sustainable energy to the world, the program faces an uncertain future. While the British government committed to pay for its share of the experiments up to the year 2020, Brexit, its planned departure from the European Union, may also lead to the UK's withdrawal from scientific agencies like Euratom, the European Atomic Energy Community. Some say this could jeopardize jet logistics and operations, and perhaps also the larger next-generation fusion experiment, currently being built in southern France. If fusion represents harnessing the physical power of the sun, a moment of darkness reflected its emotional power. An awe-induced euphoria experienced by millions as the first total solar eclipse over North America in 3 decades made its way across the United States.
It's the most unnatural natural phenomenon I ever saw.
This is a solar eclipse, and just what people witnessed on August 21st along a 70-mile wide path. First along the Oregon coast at 10:15 a.m. Pacific Daylight Time, and last in South Carolina 94 minutes later. The uncommon coupling was the most viewed and photographed eclipse ever recorded. And yet, even as the sun re-emerged from the moon's shadow, some earthly domains remained, as always, far removed from its rays. Like the cave chambers, 300 meters below Mexico's Nica mine, enormous razor-sharp crystals dwarf human explorers. While today the cave is totally submerged, previous expeditions collected bizarre life forms from these crystal giants. They call this place Hell on Earth. Temperatures climb to 135 degrees Fahrenheit, with over 80% humidity. Even with life-saving bodysuits, no visit can safely last longer than a half hour. Yet deep within this extreme environment are life forms which exist nowhere else, known as extremophiles. NASA astrobiologist Penny Boston and her team found 40 strains of mineral-eating organisms. Trapped within the crystals here, they collected sample microbes, some dormant, but alive, estimated to be between 10 and 50,000 years old, including genetically unique and previously undiscovered life forms.
Any extremophile system that we're studying actually, allows us to push the envelope of life further. And we add it to this atlas of possibilities that we can apply to different planetary settings.
By expanding the definitions of life on Earth and where to find it, Boston's findings could impact the search for life beyond our planet. On places like the protoplanet Ceres, the largest object located within the solar system's asteroid belt, and one of the scientific targets of NASA's Dawn space probe. And in February of 2017, startling and unexpected news began coming in.
My colleague found a spectral signature in her data that is consistent with or the same signature of aliphatic hydrocarbons. So here we're finding maybe the building blocks of biological material.
Seen here in red, the organic materials are thought to have originated in the dwarf planet itself. Dawn's study of Ceres also revealed evidence of water and volcanic activity, further raising the scientific profile of Ceres, no longer considered a barren rock. However, Dawn isn't the only NASA spacecraft uncovering new surprises about our solar system. Seven months after arriving in Jupiter's planetary system, the Juno Explorer became fully operational in February of 2017. Astonishing researchers with the steady stream of images and scientific data it's sending back to Earth. Jupiter is by far the largest planet in our solar system, leaving Juno with a whole lot of ground to cover. And although it is the second brightest planet in our night sky, its formation and composition have left us in the dark. Previous NASA missions have given us some understandings of its moons, small dust rings, and atmosphere. But we've not been able to see past the Van Gogh-like swirls of dense red, brown, yellow, and white clouds that paint the planet. At least, not until now. Each individual image is awe-inspiring, especially those captured when Juno came within 5,000 miles of Jupiter's Great Red Spot, the planet's most famous storm. Poring over data from Juno's microwave radiometer, scientists hope to learn more about what powers the tempest and how it differs from other Jovian storms. This critical instrument measures 6 distinct ranges of thermal radiation as it peers more than 300 miles beneath Jupiter's clouds to create a three-dimensional model of Jupiter's atmospheric environment.
So the first time we're looking inside of Jupiter with into the interior, and what we're seeing is that it doesn't work at all like we had predicted. Almost every model that has the interior motion, how the magnetic field, the gravity field, how the deep atmosphere works, it's all different.
Current modeling estimates that the cloud cover is roughly 30 miles thick. Below it, there lies a 13,000-mile layer of swirling hydrogen and helium that changes states from gas to liquid as it nears the center, leading to a 24,000-mile deep sea of metallic hydrogen.
And if we can probe it and work out the abundance of elements in it, hydrogen, helium, the higher elements as well, and work out roughly what that mix is, it'll tell us something about not only how Jupiter was formed, but how the solar system might form.
If there is a bunch of rocky material in the center of Jupiter, it means that in the early solar system, before Jupiter formed, that rocky substances were probably coming together and Jupiter got built around those. It could be that Jupiter was built without any of those and that it just collapsed sort of like the sun and there is no rocky material or core of heavy elements in the center.
Strangely though, gravity data collected so far points to a new possibility. A somewhat larger than previously thought and perhaps partially dissolved core, leaving Jupiter experts with more questions than answers.
We're putting the pieces of the puzzle together and it's exciting, but we don't have the whole picture yet.
Juno's primary mission is scheduled to continue until February 2018. But this past year, NASA saw another of its extraordinary explorers come to the end.
And we are in the atmosphere.
As the Cassini space probe plummeted into Saturn's atmosphere in a fiery death spiral.
Roughly 1 minute to loss of signal.
The culmination of the craft's revolutionary scientific quest.
Call loss of signal at 115546.
The signal from the spacecraft is gone.
Congratulations to you all. This has been an incredible spacecraft, and you're all an incredible team.
She has rewritten the textbooks about Saturn, the rings, the moons, Titan. So many things have changed because of Cassini.
From its launch 20 years ago to its bold grand finale, the Cassini-Huygens mission has unveiled some amazing discoveries. Saturn is ablaze with storms of unimaginable force. The place crackled with giant lightning strikes. The rings are even more dazzling than imagined, stretching across hundreds of thousands of miles. They're made of particles of pure water ice, some microscopic, some the size of mountains.
They break apart and they reform, so there's this beautiful cosmic dance going on inside the rings.
Cassini also carried a little lander called Huygens, which became the first probe to land on a moon other than our own. Its target, Titan, because of its atmosphere.
And as those first pictures came back, we just saw more and more haze and fog and haze and haze, until finally the probe broke through that haze and we got to see the surface of Titan for the first time.
Next, Cassini then captured giant jets of water spewing hundreds of miles into space from the Tiger stripes, shooting out at 1,200 miles per hour, vaporizing and then freezing. Back on Earth, Cassini's stunned controllers quickly reprogrammed the probe to fly right through the jets, collecting particles. And what they found was even more stunning. Organic molecules, the basic building blocks of life.
Enceladus is really special. It's giving us free samples.
Because the geysers are erupting, and they could guide the spacecraft very close and look to see if there's water there, and there is water. Here on Earth, wherever there's liquid water, whether it's deep in the ocean and very hot, or in rocky places or in ice, there's microbial life. So it certainly suggests microbial life could have evolved on Enceladus because it has all the properties that the Earth had when life began here.
NASA controllers plotted the probe's deadly descent into Saturn's atmosphere. Productive until the end. Cassini relayed detailed information about the planet's environment. And then she burned like a meteor and vaporized. Scientists will build on Cassini's contributions as the search for extraterrestrial life continues within our solar system and beyond. Perhaps around the star system 39 light years away, known as TRAPPIST-1. The first place found, NASA announced, to have multiple planets. 3 here, circling a single star inside the habitable zone, where liquid water can exist.
Well, with this discovery, we've made a giant accelerated leap forward in the search for habitable worlds and life on other worlds, potentially speaking. The TRAPPIST-1 system has really captured our imagination because with this amazing system, we know that there must be many more potentially life-bearing worlds out there just waiting to be found.
Earth-like in size and temperature, these 3 faraway worlds suggest endless possibilities.
The discovery gives us a hint that finding a second Earth is not just a matter of if, but when. These questions about are we alone are being answered as we speak in this decade and the next decades. So I'm really excited about this.
It's been an astonishing year for sure. And as our universe reveals more of its secrets, far out in space and closer to home, our foundation of knowledge will continue to grow, promising ever more to come.
$4.6 billion years ago, our sun started to form about 2/3 of the way out on one of the spiral arms of the Milky Way. Our sun is a third-generation star, starting from gaseous clouds and dense nebulae containing many heavy elements. It condensed under the inexorable pressure of gravity until it was hot and dense enough to experience nuclear fusion at its core. As stars go, our sun is an average yellow star. But it is so massive that it contains 99.8% of all the mass in the solar system. Its radiant energy supports almost all life on Earth, and it drives Earth's climate and weather. It is almost 900,000 miles in diameter. It has a core temperature of about 15 million degrees, and its surface temperature of about 6,000 degrees. The sun will be fairly stable over the next 5 billion years, at which time it will enter its red giant phase. It will expand enormously so that its outer layers will reach the current orbit of Earth, giving it a diameter of almost 200 million miles. After that, it will live a few billion more years as a white dwarf. Mercury is the smallest planet in our solar system. It is only about 3,000 miles in diameter and has a surface that is pockmarked with craters like our own moon. It is the innermost planet and has an elliptical orbit that takes it within 28 million miles of the Sun at its closest approach, and out to 43 million miles at its most distant. It takes Mercury 88 days to orbit the Sun. And figure this out, sports fans. Although it rotates once every 59 days, the day on Mercury is 176 Earth days long. Oh, it doesn't really have a tail. We added the one in the video to make it easier to see and to show its orbit. And although the scale is correct for the size of the Sun relative to Mercury's orbit, we are showing the planet 100 times larger than it would be if it were to scale as well. Except for the Sun and the Moon, Venus is the brightest object in the sky. And since it is closer to the Sun than we are, it shows phases like the Moon. Shrouded in permanent clouds, Venus rotates on its axis every 243 days, and it rotates backwards from the other planets. It is only slightly smaller than the Earth, and it orbits the Sun every 225 days, at a mean distance of 67 million miles. But its surface is terribly inhospitable. The atmospheric pressure at the surface is 92 times that of the Earth, similar to the pressure a half a mile down underwater. Its temperature is a balmy 900 degrees Fahrenheit. All in all, not a good vacation spot. Our Earth is 8,000 miles in diameter and rotates on its axis, causing sunrise every day. It is the largest of all the planets that have a solid surface, and it possesses an unusually large moon for a planet of its size. Since the moon circles the Earth, we think of the Moon's motion as circular. But since the Earth-Moon system revolves around the Sun at about 65,000 miles per hour, the Moon's motion in the solar system isn't much different from our own. At 93 million miles from the Sun, the Earth is the third innermost planet, and is the only place in the solar system that we know of that has liquid water. Mars is the planet most similar to Earth in terms of habitat. Although smaller than Earth and Venus, it has a thin atmosphere and probably had liquid water on its surface in the past. This attracts our interest and has prompted us to send a plethora of probes. It has 2 orbiting irregular-shaped rocks graciously called moons, which are probably captured asteroids. A day on Mars lasts about 24 hours, very comparable to our own. The volcano called Olympus Mons, or Mount Olympus, is the highest known mountain in the solar system. It is an extinct volcano and is over 3 times the height of Mount Everest. Mars is the 4th planet from the Sun and completes its orbit every 2 Earth years. Jupiter is huge. If it had only been a little larger, it could have become a brown dwarf star circling our Sun. It is a gas giant and has no solid surface. Its atmosphere forms bands of poisonous clouds that circle the planet in opposite direction. The giant red spot is a huge storm that has been raging for hundreds of years. 4 of its many moons are so large that Galileo spotted them with his primitive telescope in 1610. In addition to moons, all of the gas giants have rings, but Jupiter's rings are so faint they are not visible. The 5th planet out, Jupiter orbits the Sun at a distance of 480 million miles and takes almost 12 years for one complete circuit. Notice the large separation between the orbits of Jupiter and Mars. This is the realm of the asteroid belt. It is the debris of a planet that failed to form because of Jupiter's gravitational influence. Saturn is the 2nd largest of the planets. Only Jupiter is larger. Like all the gas giants, it has a system of rings. And the rings of Saturn are glorious. Like Jupiter, Saturn also has dozens of moons, and one of them is particularly notable. Titan is the 2nd largest moon in the solar system, and it possesses an atmosphere remarkably like Earth's. It is primarily composed of water ice and rocky material. It is even possible that under the clouds and surface ice, Titan has liquid water and maybe even microbial life. It is 50% larger in diameter than our own moon and 80% more massive. Saturn takes 29 years to orbit the Sun, and does so at a distance of 890 million miles. Uranus rolls on its side. It is an icy giant of a planet, the third largest in the system. Like the other giants, Uranus has a ring system and numerous moons. It is the 7th planet out, and it orbits the Sun at a distance of 1.9 billion miles. A year on Uranus lasts 84 Earth years. Because of its extreme axial tilt, seasons on Uranus are worth a look. At the time near the solstice, one pole continually faces the Sun, while the other faces away. Only a narrow strip near the equator experiences Uranus's 17-hour day. At the other side of Uranus's orbit, the orientation of the poles is reversed, so each pole gets 42 years of continuous day, followed by a 42-year night. Okay, let's head to a point high over the ecliptic, so we can see the relative sizes of the orbits of the sunward planets. Neptune is a blue world. It is the smallest of the giant planets in our system, but still 30,000 miles in diameter. Since the demotion of Pluto, it is the furthest planet from the Sun. Neptune's rings are very faint, and of its 13 moons, only Triton is massive enough to be round. It rotates every 16 hours and orbits the Sun every 165 years at a distance of 2.8 billion miles. Pluto is now deemed a dwarf planet and a member of the Kuiper Belt. The Kuiper Belt is a region of the solar system that extends just beyond the orbit of Neptune, at about 2.8 billion miles out to about 5 billion miles. Like the asteroid belt, it is crammed with many small bodies orbiting the Sun, most of which are frozen methane, ammonia, and water. Here's a size comparison. Earth, Ganymede, Titan, our Moon, and several bodies from the Kuiper Belt. Currently, the largest known Kuiper Belt bodies are Eris, Pluto, Sedna, and many more without formal names like FY9 and EL61. A day on Earth is a deceivingly simple concept. Today we'll examine that day on Earth in detail, perhaps uncovering a few surprises. A day is the length of time it takes the Earth to spin 360 degrees on its axis. Or is it 361? Here is a simple model showing the Earth, the Sun, and some background stars. The Earth travels around the Sun in an ellipse, with the Sun at one focus. The model, of course, is not to scale. Let's begin our examination at noon one day. The Sun is directly above the red line. That will be our reference point. Watching from a high vantage point, we see the Earth complete 360 degrees of rotation. But during that time, the Earth has also moved a bit in its orbit. So even after a 360-degree turn, the Sun is not directly above the same point on Earth that it was at the beginning of the spin. It is not noon of the next day. The red reference line needs to spin a little more than 360 degrees to get us to noon. The 360-degree rotation is called a sidereal day, while the noon to noon rotation is called a solar day. Earth orbits the Sun once for about every 366.26 sidereal days, and once for every 365.26 solar days. Not only that, the length of the solar day varies throughout the year, and for two different reasons. First, because of its orbit is an ellipse and not a circle, the Earth moves faster when it is near the Sun and slower when it is further from the Sun. So the little extra amount of rotation that the Earth needs to do to get from noon to noon changes throughout the year. Second, because the Earth is tilted on its axis, the little extra rotation to get from noon to noon is largest at the solstices and smallest at the equinoxes. So solar days grow progressively longer as we move from the equinox, March and September, to solstice, June and December. And did we mention the Earth's spin is slowing down? And the length of the solar day is increasing due to gravitational tides between the Earth and the Moon? The length of the mean solar day is increasing at a rate of approximately 1.4 milliseconds every century. 2 billion years ago, there were about 750 days in a year. Now let's talk about daytime. That period out of 24 hours when it is light outside. Day versus night. Due to refraction and scattering of light by the atmosphere, there can be daylight even when the sun is slightly below the horizon. But day length is usually about the sun's disk being on or above the horizon. So the day begins the moment the sun's disk appears during sunrise, and ends the moment the sun's disk disappears during sunset. At the equator, daytime and nighttime are equal to within a few minutes. But at distances north and south of the equator, the length of the day varies with the season, with the longest and shortest days being on the solstices. At the poles, once the sun has risen, it stays up for 6 months before it sets again. And during the course of each day, it travels in a complete circle around the edge of the sky. Because the Earth travels at different speeds in its orbit, the sun is north of the equator for almost 4 days more than half the year, and the length of the average day in the northern hemisphere exceeds the length of the average day in the southern hemisphere by a few minutes. In the northern hemisphere, the Arctic Circle is the southernmost latitude where 24-hour daylight can occur at least 1 day in a year. In the southern hemisphere, the Antarctic Circle is the northernmost latitude where 24-hour daylight can occur at least 1 day in a year. And daylight savings time is like the old man who cut off one end of the blanket and sewed it on the other end to make it longer. A year on Earth is measured by one complete trip around the sun. Seems simple enough, but there is a problem. The Earth doesn't travel in a path around the sun that returns to its starting point. So how do we know when a year starts or ends? Well, one way, called a sidereal year, measures our orbit against the distant stars. As viewed from the Earth, our orbit causes the sun to appear to move through the constellations of the zodiac on a path called the ecliptic. And when the sun returns to its starting point, a sidereal year has passed. This motion is difficult to observe directly because the stars cannot be seen when the sun is in the sky. However, if you look at the sky before each dawn, the annual motion is very noticeable. The last stars seen to rise are not always the same, and within a week or two, an upward shift can be noted. As an example, in July in the northern hemisphere, Orion cannot be seen in the dawn sky, but in August, it becomes easily visible. Measuring a year this way gives a period that is 365 days, 6 hours, 9 minutes, and 10 seconds long. Another possibility is to measure the year against the passing of the seasons. Because of the tilt of the Earth on its axis, the position of the sun in the sky changes from day to day throughout the year. If we were to take a picture of the sun at noon regularly throughout the year, we would see the sun moving on this path called an analemma. On the days in its orbit when the Earth is at a maximum tilt towards or away from the sun, the length of the daylight is at a maximum or a minimum. These days are called solstices, and the sun will be at the top left or bottom right of the analemma. On the days when the Earth's tilt is perfectly sideways to the sun, the day and night are equal in length. These are the equinoxes, and the sun will be at a latitude-dependent position in the analemma. When the sun goes from one vernal equinox to the next, a tropical year has passed. Measuring this way gives a year that is 365 days, 5 hours, 48 minutes, and 46 seconds long. The length of a year on Earth is affected by several gradual and cyclical changes in its orbit and its tilt. First, there is the precession of the Earth's axis. Over a period of about 26,000 years, the Earth's axis traces out a circle in the sky. One result of this is that the North Star changes over time. Right now, the Earth's axis points towards Polaris. 5,000 years ago, the axis pointed to a star in the constellation Draco. And 12,000 years ago, the brilliant star Vega was the pole star. And because of the 26,000-year cycle, Vega will be the pole star again in 14,000 years. The precession of the equinoxes is caused primarily by gravitational forces of the Sun and the Moon acting on the Earth. While the axial tilt is the primary cause of seasons on the Earth, the distance from the Sun, which changes throughout the year because of the elliptical shape of the Earth's orbit, contributes a small bit of temperature variations throughout the year as well. When the axis is aligned so it points towards the Sun during perihelion, one hemisphere will have a greater difference between the seasons, while the other hemisphere will have milder seasons. The hemisphere, which is in summer at perihelion, will receive much of the corresponding increase in solar radiation. But that same hemisphere will be in winter at aphelion and have a colder winter. The other hemisphere will have a relatively warmer winter and cooler summer. When the Earth's axis is aligned such that aphelion and perihelion occur near the equinoxes, the northern and southern hemisphere will have similar contrast in the seasons. At present, perihelion occurs during the southern hemisphere summer, and aphelion is reached during the southern winter. So the southern hemisphere seasons are somewhat more extreme than the northern hemisphere seasons when other factors are equal. In addition, the gravitational effects of other planets cause the ellipse of our orbit to slowly spin around the Sun. It takes about 112,000 years for the ellipse to revolve once, relative to fixed stars. When considered together, the two forms of precession add, and it takes about 21,000 years for the solstice to go from aphelion to aphelion. The dates of the perihelion and the aphelion advance each year on this cycle, an average of 1 day per 58 years. The eccentricity of the Earth's orbit is a measure of how round or how oval the orbit shape is. Over thousands of years, the eccentricity of the Earth's orbit varies as a result of gravitational attractions among the planets, primarily Jupiter and Saturn. The orbital eccentricity cycles with a period of roughly 100,000 years. As the eccentricity of the orbit evolves, the semi-major axis of the orbital ellipse remains unchanged, so the length of the sidereal year remains unchanged. As the Earth travels in its orbit, the duration of seasons depends on the eccentricity of the orbit. When the orbital eccentricity is extreme, the seasons that occur on the far side of the orbit are substantially longer in duration. In addition to axial precession, there's the axial tilt, the angle the Earth's rotational axis makes with its orbital plane. It is currently about 23.4 degrees and is declining. This tilt varies from 22.1 degrees to 24.5 degrees. It makes one complete tilt and back every 41,000 years. This change in tilt is directly related to ice ages on Earth. The last maximum tilt occurred in 8700 BC, and the next minimum tilt will happen in 11,800 AD. The inclination of Earth's orbit drifts up and down relative to the present orbit, with the cycle having a period of about 70,000 years. And the orbit also moves relative to the orbits of other planets as well. By calculating the plane of unchanged total angular momentum of the solar system, we can define the orbital plane called the invariable plane. It is approximately the orbital plane of Jupiter. The inclination of the Earth's orbit has a 100,000-year cycle relative to the invariable plane. This 100,000-year cycle closely matches the 100,000-year pattern of ice ages. A year on Earth is directly determined by all the various orbital motions of the Earth. So, if someone tells you how many years old they are, you might ask them, is that sidereal, tropical, or anomalous years? Want to see something really big? Well, watch this. Our starting point is our own moon. We've seen men walk on the moon, and it's pretty big. But even the smallest planets are bigger. Here are Mercury, Mars, Venus, and Earth. And the gas giants in our solar system are huge in comparison. Here are Neptune, Uranus, Saturn, and Jupiter. And of course, our sun makes even Jupiter seem small. But let's look at some really big stars. Here's Sirius, and Pollux, and Arcturus, and Aldebaran, and Rigel, and Deneb, and Antares, and Betelgeuse. And the largest star we currently know about is VY Canis Majoris. On this scale, our sun would be 1/10 the size of the tiny little dot you see to the left. We know mass distorts space. We know light is affected by gravity. And we know Einstein's theory of general relativity makes possible one of the strangest objects ever imagined by physicists. If you could create a large enough distortion in space-time, by placing enough mass in a small enough space, you could create a region of space-time so strongly curved that nothing, not even light, could escape it. And since nothing can travel faster than the speed of light, anything that entered this region of space-time would be trapped there until quantum mechanical effects allowed it to escape. Black holes can come in any size and have any mass. All that is required is that enough mass can be concentrated to the point where it collapses under its own gravity. Stellar mass black holes are formed when stars 20 or more times the size of our own sun finally run out of fuel in their cores. They rapidly cool and collapse, and the shockwave from the collapse blows the outer layers of the stars to bits in a colossal explosion called a supernova. But the small, dense core of the star can remain bound together by the force of gravity. As it continues to collapse inward under its own weight, the atomic particles of the core are smashed together until all that is left is a black hole. In its center lies the singularity, the mass of an entire star crushed into a single point in space. Surrounding that is an invisible shell called the event horizon. This is the cosmic point of no return. Once inside the event horizon, nothing, not even light, can escape except through quantum mechanical processes. Supermassive black holes may contain billions of times the mass of our sun. These monsters lie at the center of every large galaxy. Micro black holes have tiny masses at which the effects of quantum mechanics are very important. Black holes of this type have been proposed to have formed during the Big Bang and would quickly evaporate due to said quantum mechanical effects. At the end of their life, it is believed that they would emit a sudden burst of energetic particles, but no such bursts have been detected as of 2008. We can never see into or directly know about what happens inside the event horizon of a black hole. In effect, any object that crosses this imaginary line has left our universe for good. But if nothing, not even light, can escape a black hole, then how do astronomers manage to detect them? It is possible to imagine spotting a solitary black hole by observing the bent starlight from behind it. But a better chance of detecting one would arise if they were not alone in space, but accompanied by another star. This black hole is drawing matter from a companion star, which orbits it at a distance safely outside the event horizon. As the gas spirals into the black hole, it heats up and emits huge quantities of high-energy radiation. Intense radiation emerging from a small area, or stars orbiting small invisible companions, these are telltale calling cards of a black hole. $12.5 billion years ago, the universe was littered with the remains of first-generation stars, and billions of second-generation stars were born from these clouds. Small groups of these new stars were drawn to each other gravitationally and merged to form ever larger and larger groups. Our own galaxy, the Milky Way, is an example of a spiral galaxy born in this early era. Today, it contains about 200 billion stars and is still growing as it absorbs small neighboring clusters of stars. The center of our galaxy is in the direction of the constellation Sagittarius. And like most large galaxies, there is a monstrous black hole at the center. The disk of our galaxy is about 100,000 light years across, and on average is only about 12,000 light years thick. Our own sun is a third-generation star, and is located about 2/3 of the way out on the spiral arm named Orion. We are about 26,000 light years from the center. The Milky Way is a member of a group of 20 or 30 galaxies and star clusters called our local group. The largest galaxy in this group is our sister spiral galaxy, Andromeda. Is it possible for distant galaxies to be moving away from us faster than the speed of light? And if it is, would it be possible for us to see them? Surprisingly, the answer to both questions is a resounding yes. How is that possible? How can something travel faster than the speed of light? Today we will try and paint an accurate picture of the universe based on the lambda cold dark matter model, which is the best cosmological model today. Once we have painted that picture, the answers to our questions will be straightforward. Let's assert that some kind of space-time quantum foam sort of something existed before our own universe began, before our Big Bang. Then we simply let Heisenberg's uncertainty principle go to work for us. If we look at the tiniest speck allowed by quantum mechanics, a small volume with a Planck length as its linear scale, the speck would have a volume of 10 to the minus 99 cubic centimeters. And the largest amount of mass or energy that we could put in this volume, without it becoming its own black hole, is about 1/100,000th of a gram. Interestingly, the uncertainty principle allows this much stuff to be created out of nothing for as long as 10 to the minus 43 seconds. Not a very long time, but it will prove to be enough. Because if that much energy is created in the form of a certain type of scalar field, then we have just successfully created a universe. The best model of how our early universe grew after that initial quantum fluctuation created it includes inflation, a period when the scalar field divides space into a brief period of extreme exponential expansion. During inflation, space erupted from its tiny beginnings into an unknowably huge volume. This enormous expansion generated an enormous amount of gravitational binding energy, at least 10 to the 85th grams. And this was counterbalanced by a corresponding group of positive energy in the scalar field. What began as a mere fraction of a gram of energy has now become 10 to the 85th grams. This is a huge number, large enough to account for all the matter and energy that exists today. But notice that the total energy in the universe is within a quantum fluctuation of equaling 0. As a byproduct of the enormous growth of space during the inflationary period, tiny quantum fluctuations grew into macroscopic fluctuations in the density of the scalar field, making it ever so slightly lumpy. This lumpiness provided the seeds for the formation of stars and galaxies and all the structure we see in the universe. At the end of inflation, the temperature throughout all of space was still enormously hot, But as space continued to expand, it cooled, and the energy of the scalar field, which now filled all the new and enormously huge volume of space, decayed into dark matter, and dark energy, and normal matter. The photons and quarks and electrons, which in turn settle down into the protons, neutrons, and atoms that populate the universe today. After about 380,000 years of expansion and cooling, charged particles got together to form neutral atoms. And suddenly the photons that were bumping into charged particles every second or two were free to zip unhindered across space. This is the origin of the cosmic microwave background that we see today. Let's let this volume of blue dots represent all of space at that era. Then let's focus our attention on this tiny portion that has a radius of about 42 million light years. This is the region that will be all of our observable universe in 13.7 billion years. Our Earth will form somewhere in the center of this region in about 9 billion years. But we have a lot of expansion to experience first. Imagine that you are standing on a 100-meter track and someone 99 meters away is going to walk toward you. There's the starter's pistol, and the walk begins. But there's a problem. The track is stretching, growing longer as he walks. He takes a 1-meter step every second, but the track grows 1 meter for every 100 meters every second. After 10 seconds, the walker has taken 10 steps, but the remaining 89 meters has grown so that he still has 98 meters from you. Another 10 seconds, and he's still almost 97 meters away. It will take him 460 seconds, but he will eventually reach you. And during that time, the track is stretched so that it is now 10,000 meters long. The other end of the track is now moving away from you much faster than the walker can walk. If he had to start there now, he would never get here. And the question of how far he walked is ambiguous. We could say he walked 99 meters because that was the distance at the beginning, or we could say that he walked 9,900 meters because that was the distance at the end, or we could say 460 meters because that is his normal speed times the time it took. The expanding universe exhibits the same characteristics. Light from the edges of the 42 million light-year sphere began their journey to the spot where the Earth will develop about 13.7 billion years ago. But during the trip, the intervening space multiplied itself 1,090 times. And now the spherical shell from which the light began is about 46 billion light years away. This is the farthest into space we can see right now, and it is called our particle horizon. 100 million years after inflation, the first stars formed. They were massive giants that formed in every region of space, including our little sphere of observable universe. Those that formed on a shell a little inside our expanding particle horizon are just visible today. The light from these primitive giants has been traveling over 13 billion years. And the shell of space where they formed is now over 36 billion light years away. So light from the microwave background was emitted from a distance of just 41 million light years away. and that distance is now 46 billion light-years. And light from the earliest stars was emitted from a distance of 1.5 billion light-years, and that has grown to 36 billion light-years. Due to the faster-than-light expansion of space in those early years, the light was actually moving away from us for billions of years before the slowing expansion allowed it to start moving towards us. Light we see today from some distant galaxies that was emitted from 5 to 6 billion light-years away comes from objects that were the most distant at the time the light was emitted. Massive objects like the Earth and the Sun, that are gravitationally bound to one another, can overcome the expansion of space between them. Space is expanding in our system, but the distance from the Earth to the Sun does not change because of this expansion. Why? Because as space expands, the Earth's orbit continually adjusts to keep the Earth at the correct distance that is demanded by the law of gravity. This is also true for stars inside a galaxy that are gravitationally bound, and is true even for local clusters of galaxies. As space expands, the distance between the bodies constantly adjusts to comply with the laws of gravity. The wavelength of light from distant objects is shifted toward the red end of the spectrum if they were moving away from us. And the expansion of space is measurable by measuring the redshift. And unlike the Doppler redshift, the cosmological redshift says nothing about the recessional velocity of the emitting object either at the time the light was emitted or at the time the light was received. Hubble's law says the further away an object is, the faster it is receding without limit. So, there are always objects far enough away to be receding faster than the speed of light. Objects we see with a redshift of about 1.46 are moving away from us at the speed of light, and all objects with larger redshifts are receding faster than the speed of light. Most objects in the extended universe are traveling away from us with velocities fast enough that we will never see them. In effect, we have an event horizon, and events beyond our event horizon are effectively unknowable to us. Objects that have a current redshift of about 1.8 are currently about 18 billion light-years away, and are now crossing our event horizon, never to be heard from again. Finally, this is a time sequence of the evolution of our universe. Big Bang, followed by inflation, reheating or the birth of matter, birth and death of the first stars, and the ongoing formation and growth of galaxies. When we look out into the universe, we are looking backwards in time, looking at the universe as it was when it was a lot smaller and a lot younger.